Hello students, let us take a look at Hydroxy Compounds class exercise 2. I hope you have gained valuable insights from the review of exercise 1 earlier on. Okay, so we'll take a look at question 1, which is a Cambridge question back in 2013. It belongs to the old syllabus, but is still highly relevant to our current curriculum. Okay, so we have vanilloids. They are a class of compounds found naturally in spices such as ginger and cloves. The general structure and some reaction of vanilloids are shown below. The R group represents a side chain. Okay, so since they say a side chain, probably not very important. Now we'll take a look at vanilloids. Okay, I'm just going to highlight the important functional group. We have a phenolic OH over here and O-methyl group. Okay, we are probably at this stage quite familiar with OH because OH is strongly donating. But what about O-methyl group? Okay, so we'll toggle to the data booklets. Okay, under section 8, this is on the directing effects of groups in aromatic substitution reaction. So notice that this is G is a group. Okay, so if you look at the second row over here, okay, we have OH or OR. So R is an alkyl group. So both OH and OR are strongly activating group. Of course, it's not being written in the data booklet as strongly activating, but based on what we learned from the lecture notes, we know that because of the lone pairs of electrons on R that partially overlap with the pi electron cloud in the phenol ring, then that will help to greatly increase the electron density, making the phenol ring more susceptible to electrophilic attack. Okay, so OH and OR are strongly activating group as compared to LQ. Okay, so with this knowledge in mind, we probably need them in subsequent processes in determining, we need to determine the substituent effect. Okay, so we are not very sure at this stage, but we'll take a look at and see what it entails. Okay, and then after that, the question actually asks us to identify reagent A and B. So if you take a look at reagent A, right, we don't know what it is, but you know that it involves deprotonation, okay, of the phenolic OH. Okay, so in that case, if it involves deprotonation, my reagent A can simply be sodium hydroxide, because you know that phenol is acidic enough to deprotonate, to be deprotonated by sodium hydroxide. Okay, yeah, but what is often used in the industry, right? Because sodium hydroxide is in an aqueous medium, and sometimes aqueous medium might be a little bit tricky, especially for organic reagents. So in the industry, they prefer, or in the research lab, they actually prefer to use sodium. Okay, this also appears in your lecture notes. So you can simply just use sodium solid. Yeah, of course, if you use sodium, right, you need to ensure that there is opening in your reaction vessel to allow the hydrogen gas to escape. If not, pressure will build up and it can be quite dangerous. Okay, then for reagent B, if you take a look at what happens, this is sort of the groups being introduced. So if I'm going to draw the side chain out, okay, so I have a OCH3, I have R, and then I have an oxygen here, and a C double bond O, like this. Okay, so clearly this portion is over here. And then I am forming an ester linkage. So if I'm going to form an ester linkage, what's the first thing that comes to your mind is probably a carboxylic acid. But if you take a look at your notes, right, phenol doesn't react with carboxylic acid, or it doesn't react so readily. Yeah, because of the fact that the lone pairs of electrons is partially delocalized into the phenol ring. So that makes the phenol a relatively weak nucleophile. Yeah, so in order to enhance this particular reaction, right, we can't use phenol. So we have to use, as in we can't use a normal carboxylic acid to react with phenol. So we have to use a more reactive version of the carboxylic acid. So that part you will learn under carboxylic acid derivatives. But I'm pretty sure in your lecture notes, they also mentioned that in order to produce ester, right, in addition to carboxylic acid, you can also use a reagent known as acyl chloride. Okay, so we can use acyl chloride over here. So I'm going to draw out acyl chloride. Maybe I'm just going to draw the functional group first. Okay, a C double O. Yeah, so instead of OH, I replace it with a Cl. Yeah, so acyl chloride and phenol will undergo condensation reaction, and it will lead to the production of HCl. Yeah, so it will appear as white fumes. Okay, next, we are supposed to suggest the structure to organic product C. Yeah, so take note that we are using dilute nitric acid. Yeah, so in this case, this is a characteristic reaction of phenol where we only want mono substitution. Yeah, however, we have a little issue. The little issue is that if we are looking at simply directing effect, actually any of this position works. The reason is because the OCH3 in fact is a little bit more electron donating than OH, than a phenolic OH. Yeah. So if you simply look at electron donating effect of the OCH3 simply by electronic effect. So this OCH3 can direct the electrophile here or here. Okay. And of course, phenol will be able to direct the electrophile to over here. Okay, but if you look at steric demand, okay, so for steric demand, this portion is out because it is sort of being placed in between, or rather the electrophile will need to experience steric repulsion between two groups, the R group and the OCH3. We don't know how big the R group is, of course, so I will probably not put the electrophile to be approached from in this particular direction. Then what about here? Yeah, this part is possible. So it really depends on the R group. If the R group is sufficiently huge, then probably appearing or being directed at the place I place my tick over here, right, will be slightly more probable than over here. Okay, so I just put it as a double tick. Yeah, so probably here will be more probable than the place I put a double tick. Yeah, so because of that, then I'm going to draw my product C as just a phenolic OH, okay, and a O methyl group, OCH3, and an R group over here, and an NO2. Okay, so NO2 I'll write it as O2N. Why is that the case? Because if I'm going to expand this out, right, the O2N out. Okay, so I'm just going to expand it for you to see. Okay, it actually looks like this. There's an N here, double bond O, and a dative covalent bond towards O. Yeah, so if you want to know how to draw NO2, right, probably one thing that will help you is to draw the dot and cross diagram for NO2, and then that allows you to see why does it look the way it does. Okay, so NO2 looks like this. So there's a dative covalent bond from N to O, and then my nitrogen is a radical. So this radical single electron, right, will form a bond with the sigma with the carbon I circled over there. Yeah, so that's why it's a single bond over there. Yeah, so for those of you who learn formal charges, right, then you will not put it as a dative covalent bond. You will probably put a normal bond like this, and with a plus and a minus. Yeah, so it really depends on how familiar you are with dative bond or how familiar you are with formal charges. So of course the preference is to put formal charges, but in H2 curriculum we don't usually incorporate formal charge in our answers. Okay, next, bromine can be used to confirm that vanillite contains a phenol group. State two observations that you expect to see when a small amount of aqueous bromine is added to a sample of vanillite. So over here is a small amount of aqueous bromine. Yeah, so just a very small amount, which means kind of like the limiting reagent over here. Okay, so they wanted two observations, right? So the first observation, I would expect the yellow-orange aqueous bromine to decolorize. Okay, so in case you forget the color of aqueous bromine, right, we can scroll down to the data booklet, the last page, or rather the second last page over here, right at the end, the color of halogens. Yeah, so if you look at the third column, you will be able to see that bromine color in aqueous solution is orange. Okay, or in our lecture notes we describe it as yellow-orange for dilute solution. Yeah, so in case you don't know the color, please scroll to the second last page. It is over there. Yeah, do not guess. Okay, so I think the first thing I want to write is yellow, orange, bromine decolorizes. Okay, the second one, some of you might be writing would be you expect the production of white PPT. But do note that the white PPT, right, we are only confident that 2,4,6-tribromophenol is white. Yeah, the others need not appear as white. It might even appear as oil. So this might not be a very good observation, but unless you have nothing to write, then probably that is something you can write. Yeah, another observation you can write would be the white fumes of HBr. White fumes of HBr. Because we are using a small amount of aqueous bromine, yeah, so I would expect the white fumes of HBr to be rather visible as compared to guessing whether a white PPT will appear. Yeah, because in this case, right, the electrophilic substitution, it might happen in all the position, here, here, and here. Yeah, but whether it will appear as a white PPT remain questionable. Okay, but of course, really depends on how Cambridge marks it. Probably they will accept even you saying that you expect white PPT to appear. I don't think they are very strict on this, but from a more practical perspective, I think the white films of HBr is likely to be more observable. Of course, the caveat is over here. A small amount of aqueous bromine is used. You can't put in a voluminous amount because if not, I'm not going to observe anything. I mean, because the white films will essentially be dissolved in water. Because if you use a huge amount, then the white films will not even have chance to appear. Right, and then finally, over D, we are required to complete the equation for the reaction with bromine by adding by balancing this particular equation. Okay, so of course, if you are looking at 2,4,6-tribromo or rather, if you are looking at substitution at this position, and this position, then you will need to write out. You need to use more bromine in this case. Yeah, but if we are just looking at mono substitution because of steric, then I'm just going to write in one bromine molecule. Okay, over here, and OH. Okay, so I'm just going to put in in the same positions as what we had earlier on. What we had earlier on for the what's that group? NO2 nitro. So I'm just going to put the Br here, and then over here is not a H2 gas. A lot of students, I've experienced marking the students writing H2 gas. It's not possible, okay, because the H will be released as a H plus, and then because of electrophilic substitution, the Br will get polarized, okay. So one of it will become Br minus. So a Br minus and a H plus, definitely you will not get hydrogen gas. Okay, so you get you will get HBr being released. Okay, so just remember that. Remember, if you focus on fundamentals, you are able to predict a lot of the products quite easily. You do not need to commit them into memory. Okay, next we look at question 2a. So for question 2a, you're supposed to explain the following observation as fully as possible. Write equations to support your answers. Okay, so phenol forms 2 or 4 nitrophenol with dilute nitric acid. Okay, whereas for methylbenzene, it forms 2 or 4 nitromethylbenzene when treated only with corn nitric acid. So in the presence of corn sulfuric acid. Yeah, so now they're asking you why is that the case? Okay, so the reactivity of phenol versus methylbenzene. Okay, so methylbenzene. Okay, so one of them I use reagents. I use dilute nitric acid. Okay, then for the case of methylbenzene, I will need corn sulfuric acid and corn nitric acid. Yeah. Why is there such a difference in reactivity? Okay, so first of all, right, we need to understand in terms of electron donating effect. Okay, is the phenolic OH more electron donating than CH3? So of course the answer is yes. After going through class exercise 1 and this particular class exercise question 1, right? Yeah. So because the lone pairs of electrons on oxygen, right, directly overlaps with the pi electron cloud, so it increases the electron density of the phenol ring by a lot. Okay, maybe not a lot, but sufficiently lah. So it is so electron rich that it can even react with a weakly electrophilic nitric acid. Okay, or from another perspective, it doesn't need an external catalyst to generate a strong electrophile. It can react even with a weak electrophile such as a nitric acid. Yeah, and it doesn't need to be placed in harsh condition. Yeah, just nitric acid at room temperature will do. Yeah, but for the case of methyl benzene, the methyl group is not that electron donating. Yeah, so therefore, right, it requires a very strong electrophile to be produced in order for methyl benzene to react with it forcefully in that sense. Yeah, so in that case, putting dilute nitric acid with methyl benzene on its own, right, they won't react, they will just mixed. So I will need corn sulfuric acid in order to generate the nitronium electrophile. So if you are able to recall, right, the role of this is to protonate. Okay, I'm just going to draw this out. Okay, so this is nitric acid. Okay, so the role of corn sulfuric acid over here, right, is to protonate the nitric acid, okay, such that I'm able to generate the nitronium electrophile that looks like this. Yeah, so because I force out a very reactive nitronium electrophile, then my methyl benzene will then be able to react with it through nitration. And in this case, it is still operating at room temperature. Yeah, but because the electrophile has already been generated, right, then I do not need to increase the temperature any further. Yeah, for the case of phenol with nitric acid, I do not even need a very strong electrophile. I just need nitric acid to be placed inside, and the reaction will continue. Okay, yeah. So over here we are required to write the balance equation, okay, or rather write equations to support your answer. Yeah, so I mean, it doesn't really matter, so I can simply just write one of the equation. I mean, I think most of you, if not all of you, can easily write this for me. Okay, so just phenol plus HNO3 equals, okay, so I'm going to get two products, of course, the two nitrophenol and then 4-nitrophenol, but I'm just going to write out the 4-nitrophenol, and then in this case plus H2O, because you know that H2O is the byproduct. Okay, you can do the same thing for methyl benzene if you wish to. Of course, for methyl benzene you need corn sulfuric acid as the catalyst. Yeah, so I'll just leave this to you, because they said write equations to support your answers where appropriate. Yeah, so in this case I'm just going to write out the nitration for phenol, and then if I want to, I can easily write out for the one involving methyl benzene. Okay, so the one involving methyl benzene, right? I will need corn nitric acid, so HNO3. For corn nitric acid, I'll represent it as L. Okay, and then of course I will have corn sulfuric acid. Okay, and of course over here I'm going to write methyl benzene out, O2N, and then plus H2O. Okay, so the corn sulfuric acid in this case acts as the catalyst and also a dehydrating agent. Okay, so finally, part B, supposed to arrange the following phenol in order of increasing pKa. So keyword here is increasing pKa. Yeah, so therefore from the strongest to the weakest acid. Yeah, because as you know, the higher the pKa, the lower the Ka, and the lower the extent of ionization. Yeah, so of course, if I'm going to place it, A is definitely the benchmark, so phenol is definitely the benchmark. Okay, and then of course, before phenol, I'm going to have a stronger acid. So the stronger acid is the one when the negative charge on oxygen can be further dispersed into the phenol ring. Okay, so with that, I will need an electron withdrawing nitro group. Okay, and the presence of an electron donating group will prevent the negative charge from further dispersing into the phenol ring. So a donating group will therefore, once an electron donating OCH3 will partially overlap. The lone pairs of electrons on O will partially overlap into the benzene ring. So that actually prevents the conjugate based negative charge from further or from delocalizing appreciably into the phenol ring. Okay, so I'm going to place it in this order, and then in order to explain it, the simplest thing is to compare between two pairs. Okay, so that will be the suggestion. So I'm just going to write out the conjugate base first. So minus, minus, minus. Okay, so I'm just going to box them up. Okay, so I'll compare these two first. Yeah, so the conjugate base of B, right, will be more stable than the conjugate base of A. So this A, this is B. Okay, why? Because the lone pairs of electrons on the negatively charged oxygen, right, is further delocalized into the phenyl ring due to the highly electron withdrawing nitro group. Yeah, so therefore it is not as negatively charged, lower tendency to attract back the H plus, more stable than phenoxide, so therefore B will ionize to a greater extent. Okay, then I can then compare between A and C. Okay, same explanation, but instead of saying that the lone pairs of electrons of oxygen can be further delocalized in the phenyl ring, I would say that because of the electron donating OCH3, the lone pairs of electrons is being prevented from delocalizing into the phenyl ring appreciably. Yeah, so therefore the negative charge is more negative for C. So C, the conjugate base of C is less stable than that of A. Yeah, so therefore C will ionize to a smaller extent. Yeah, so therefore a smaller or rather lower Ka and a larger pK value that C have as compared to B. Okay, so with that, we have come to the end of the review. I hope you have gained insights in hydroxy compounds class exercise 1 and 2. Then please look forward to further review of future class exercises.